Okay, last time we talked about what we called quote-unquote direct investigation as opposed to indirect. Indirect being geophysics, where you use some kind of proxy to understand exactly what's in the subsurface. And this is to give us the stratigraphy, the site conditions that we need to do any kind of analysis. And so last time we talked in large part about methods of drilling, and we know that in terms of methods in drilling, it matters whether you're going through soil, in which solid or hollow stem augering is one way to go, or by using just rotary drilling, not diamond drilling, but just rotary drilling is one way to go. In the case of tricone drilling, you don't get any samples, but you do get chips out of the hole, and so you have, and also in solid stem augering, you also have to guess. But in hollow stem augering, you're actually able to use the auger flights as the drill casing and sample from inside them. And so sampling is key. In drilling in rock, tricone can certainly be used, in which case you don't get samples, or you do get samples if you use diamond drilling. And so we talked about the different methods by which we do that. And so today, rather than cover that again, we'd like to talk about the kinds of sampling that we might use. So the point was that if you're putting maybe $1,000 a meter, in this one case in Montserrat we talked about, to drill a hole, probably not as much as that, probably it's a few $100s a meter to drill. If you're putting that kind of money into site investigation, you might as well get the most out of it. So getting the most out of it means sampling, to be able to make sure that what you have down there is what you have down there, and also be able to do laboratory experiments on it if needed for the kinds of parameters that we've talked about in this class. Maybe you want to leave some instrumentation in it to be able to measure things like contaminant concentrations and pressures, and be able to use that instrumentation to do well tests to measure permeabilities, which you can then link to capillary entry pressures, etc. And so it's useful to be able to get the most from these boreholes. Typically, when you go off a hole, you want to seal it if you're not casing it, because you don't want to cross-contaminate aquifers, and you may almost usually be required to do that. And so we'll talk about those methods today. And the other method of being able to figure out exactly what is in the subsurface, which works only for soil, is continuous profiling, which is geoprobe type methods, which is a brand name, but cone penetrometer testing, which allow you to get some information both on the stratigraphy as you go down below your feet, but also what the properties of that stratigraphy are. And so that's what I wanted to cover today. Yeah, so this is it. This is where we finished up last time. I didn't go through these word components, but we talked about diamond drilling. So you remember the last thing we talked about was using wire lines to be able to go down inside the hole, pull out this whole core barrel with the core that exists inside that, and leave the drill string down the hole, so you have casing that holds your hole open and you don't have to worry about anything else collapsing. So we talked about a variety of different methods of drilling. There's a useful summary slide in this material, which is this one, which merely goes through a whole bunch of these things that we talked about. Hollow stem and solid stem augers we talked about. Doing it by hand. Rotary were these drills with the tricone bits, using air or foam. Hammer drills, which are less used. Using wire line, which is only with diamond drilling. And well, all kinds of different permutations on those. But you see some of these, you get some appreciation for what drilling fluids you may use: air, water, foam, drilling mud, whether you use casing or not, whether you can go through soil or rock only, how deep you can go. Augering is to relatively shallow depths. 150 feet is relatively shallow. Certainly you can you're not diamond drilling to Marcellus depths at 3 kilometers, but you might be drilling for core, for exploration drilling. That's the standard way of looking for gold, is to use rotary coring down to a couple of thousand feet in this case. That's 600 meters. Borehole sizes, whether you can or don't get samples, whether you can also combine rotary coring with auger stem once you get the augered hole down. And the references don't apply here because you don't have that. So those are just some background information, actually, if you look at that. I remembered, actually, some of these things are better in motion, I suppose. Let's have a look at this. Is F full screen? Yeah, it is. So you'll recognize this. Let's have an undercurrent there. So you recognize this from last time. This was the rotary drilling. It's under an overpass in somewhere on the outskirts of Boston in Massachusetts. They're adding an extra linkage of pipe. The drill bit will be down on the bottom of the hole. They've added an extra length of pipe by screwing it into, a male thread into a female thread. And now with that added on the top, they'll couple the whole of the drill string up to the turntable with this connector here. The water goes down the drill string down to the bottom of the hole, and then washes the cuttings back up into here, and ultimately, I don't see it here, perhaps it's plumbed in some different way, they'll be taking the water out of here, and it will go back up into the, oh, here it is here. This is the suction that's taking the water out of here and back up into the drill string. It's going down, you see some twine here. The twine, I think, so these are tapered threads that screw into each other. So to get a good seal, I think, is just the reason for putting that twine in there, so that you can get a good liquid seal, so that you're not leaking drilling mud, which in this case, this is drilling mud. It's mainly water, but it's a very low concentration solution with mud, so a bit denser than water, but not really very much. Goes down to the end of its run, and then they'll do the same. They'll break pipe. So they'll, don't know why they're keeping on running it now. Maybe to flush cuttings back up to the surface. Looking to see if cuttings are coming out. Household sieve, we mentioned last time, right? It's how you might take cuttings to sample what's going on. And maybe there's a break in the movie, not sure. Let's roll through it a little bit, see what happens. In the coal, this is the instrument that's down the hole. And then when you want to pull pipe, you do the opposite. You pull it out of the hole, you break it off. This is light enough to be able to manhandle. If it was 20-foot segments, it's not. You pull it out. There's enough friction in the hole to have it stood there. This is the twine on the thread that seals it to be able to allow a good seal. And these 5-foot sections of pipes, by looking at it, are easy enough to manhandle and just keep on pulling it up. This collar is just a loose-fitting hole. If it's angled, then it grabs the pipe, and I guess that's the tricone bit right at the bottom. Not motorized or powered in any way. If it goes back into focus, and this is drilling in clay. This isn't rock. This is just a hard clay, and the casing at the borehole. So nothing particularly mysterious about this. So what else? We're going to talk about sampling. And so the other issue here is I'm not sure whether they're just advancing pipe or whether they're actually doing sampling. So one of the methods of sampling is if you have this open hole, you go down to the bottom of the hole where you don't have a sample, but you've pulled all your pipe, and you want to be able to take a cookie cutter of exactly what it is. And the cookie cutters come in two different modalities. If it's clay, which is what this is, you might either physically push the cookie cutter in. The cookie cutter is a 2-foot piece of tube with a very thin wall that basically goes down and twist it off to bring up a sample. Or if it's something a bit more stiffer clay, maybe weathered bedrock or sands, then you use what's typically called a split spoon, which is a thicker walled cylinder, same idea. But instead of being able to physically just put the drill turntable on top of it and push it into the bottom of the borehole, you use a monkey hammer. Don't know why it's called a monkey hammer, but you can see it's a weight of a standard weight of a cylinder of a standard weight that's raised up a certain height and then just free dropped. A couple of loops around a capstan. You pull it tight. It gives enough friction to raise the hammer. And then it drops down, and physically it's banging this thing into the ground. I think here it's just banging casing. It doesn't look to me like it's banging a tool into the ground, but it'd be exactly the same mechanism that you'd use to do that. And you can hear the ring, of course. So, and you can tell something from the ring as to what it's going through. Don't know. Does it go black? Is it all black? Yeah. We're going to advance some more pipe. Not sure what else. Same idea. We've seen it before. Actually, this is that's a sampling tube. So this brass tube at the bottom is the cookie cutter. This is the rest of the assembly in this particular case. And actually in this case, sometimes it's tough to sample things that you could imagine that if you're putting a cookie cutter down a hole that's 2 feet long to physically push into the ground, if it's long enough, if it's 2 feet long, you might expect that the stuff in there would stick in there when you twist it at the bottom to break it off at the bottom, and then when you pull it up, the stuff that has kind of been advanced into this would stay in there. If it's really loose sand, for instance, that might not be the case. You can imagine that you twist it, and then as soon as you pull this thing up, everything would just drop out of it if it's not very solid, if it's not indurated. And so this is a special kind of tool. We'll look at it. It's called a well, actually, I'm trying to think what it's called. It's called, well, this is called a Shelby tube, after its inventor, I suppose. This is a piston sampler, and basically what it is a piston that gets advanced to the very end of this tube that expels all the water that's in this tube. The whole assembly gets put on the bottom of the borehole, and then the tube is physically pushed into the soil in the bottom of the borehole, but the piston of the syringe at the bottom stays on the bottom and kind of rises relative to the brass tube. And so then what it does is it basically doesn't allow any air gap to exist between the bottom of that syringe and the soil. And so that when you withdraw it, you can pull on it to make a vacuum at the top of the airspace that would be at the top of this tube here, and therefore you physically suck the sample in and lock it in. And so it's a piston sample that's used for that. And so this is called a thin wall sample, or a Shelby tube. And so it's a tube that might be an 1/8 or a 1/16 of an inch in wall thickness, maybe 2 inches in diameter. Sharp enough on its tip to cut you if you get your finger in the wrong place. And it's just getting ready to being dropped down inside the sampling hole here at this time. It's locked on with Allen keys. The Allen keys go into the sampler and leave the wide collared holes, so you don't actually take the Allen keys out. You screw them in, and then the sampler falls off it after you've done your sampling. We've missed something here. In December, you wouldn't think you'd want to use a torch on a latex line, but it's frozen, and so it's no great problem here. And I guess we're almost at the end of this. So that's the sample coming out and being taken off the sampler. The driller getting less dirty than the driller's helper. Hierarchy in action. So those are the kinds of samples you use. So you've got a nice hole in the ground. If it's rock, you might have rock core if it's rotary drilled. If it's rock, that's the sample here. This is the end of the sample. It's actually beaten up where it's gone in, hit a rock, stone in the ground, right? It's been warped at the bottom. You might get continuous core with a diamond drill. But if you want to get soil samples from a rotary drill where there's no sampling, then this is your option. This is the piston that goes down into the top of this core and pulls up this sample. And so what would happen now is that this end would be trimmed off by cutting it back into the Shelby tube. You'd seal it by pouring molten paraffin wax on it to seal the moisture in, and then you'd pack it off back to the labs to extrude the core, to maybe do some permeability measurements on it if that was important for the project, or air entry or liquid entry pressures. There you go. Good hat, don't you think? So, warm is better than pretty, as you can imagine, right? So that's sampling. So yeah, go ahead, Shah.
Do you remember approximately how deep
that hole?
that drill?
It was only 30 or 40 feet. No, it's not very deep at all. So the whole motivation of that hole was to proof test a tool, which we'll see as we go through some pictures. A tool that was going to be used offshore in the Gulf of Mexico to be taken down a big rotary petroleum hole and to be advanced beyond the hole with a little like pencil-like probe on it that would measure the pore pressure maybe 2 or 3 feet ahead of the bottom of the hole in soft Gulf of Mexico sands, which are what the reservoir rocks are there. And to be able to use that to be able to predict pressures. Overpressures in offshore wells in petroleum reservoirs are a big problem because you have to balance the weight of mud that you have on top of them to avoid it blowing back in the hole. But so that was an environmental exploration hole to be able to try and deploy that tool 40 feet down before deploying it in a very expensive hole, maybe a few kilometers down offshore. So it's just a convenience. So this is actually a good figure, I think, to explain the things that we've talked about. These are the kinds of sampling tools together with the environments in which they might go in, going from soils all the way through to hard soils, through to soft rock and hard rock, and gives a pictorial connection with most of them. They really fall into 3 categories, I would say. Soils that are granular, that have to be really, you have to bang a tool into it. And because you have to bang a tool into it, because sands are and gravels are quite resistive, the wall of the tool is pretty thick. And it has a cutting shoe on it, which is also quite substantial. And so that when you enter it into the borehole and bang it in with this monkey hammer, you don't shatter the walls of this or buckle the walls as you push it in. It'll have water in it. This is a check valve, just a ball bearing. It'll fill with water, and so when you pull it back up the drill string, it'll have a whole bunch of water in this drill string, and if you don't want the water to wash the sample out, this is what stops all the water flushing the sample out of the split spoon. So these are typically called split spoons or split barrels because you ram them into the ground, you retrieve them, you take off this shoe, you take off this coupling here, and it breaks into 2 halves with a sand sample that's inside it. And so that's one major denomination. This is the same, a thick-walled cylinder. The reality is that the sample you get in here is completely disturbed, and so you can use it to say it's a sand, but you really can't use it as a pristine sample to use in the lab for a permeability test. So those are what you'd use in sands, gravels, maybe silts, but mainly hard soils. Shelby tubes, or thin wall samplers, you can see this, have a very sharp edge on them. Same idea, they're attached to the drill string as it's advanced down the hole. These, instead of being physically banged into the ground, are actually pushed into the ground with the drill string. Again with a check valve, so you don't wash the sample out of the system. And yeah, so those are the main kind. This is the idea of this one with a piston sampler. Piston goes down to the bottom. This goes against the bottom of the borehole. And then you physically push the cookie cutter into the ground by pushing here. And the sampler piston kind of advances up inside it. And so that when it's almost in, the piston will be up here. There'll be a sample in here the rest of the way. And if you now pull on the piston to make a vacuum between the sample and the piston, you provide some means to actually have a good chance of retrieving the sample when you pull it up out of the hole. So there's no need for check valve here because you've kind of excluded water out of here in this particular case, and so that's the mechanism by which it'll work. This is a thinner diameter split barrel, split spoon. This is a core barrel. This is a wireline core barrel. So this is for what would be on a rotary drill that's turning. Again, with a wire line in this particular case, you can see kind of hopefully you can see shades of exactly the wire line that would be able to take the sample out through here. And this is a core catcher. So if you imagine a comb that you comb your hair with, and you take that comb and you bend it around into a circle, that's exactly what this is. It's a stainless steel core catcher that allows the core to go in, but as it tries to drop out, as you retrieve it, it'll grab it and stop it coming out. So it's basically a comb. There's nothing stronger really than a comb. It kind of works as a ratchet. And a full-fledged diamond bit would be this. This is a single wall core barrel. Looks like you have to pull all the core string to be able to withdraw it, but again has a bit on here. It's rotating, it's grinding the rock away, and this would be what you'd use in soft rock and hard rock combined. And indeed, you'd use something like this in that as well, as a wire line. So really just three denominations. Sands and gravels, you have to bang it in, so you need a thick wall core barrel that's just physically banged into it. You get a disturbed sample. You can get a pristine sample in clays if you use this Shelby tube or a thin wall sampler. The thin wall doesn't really push the material aside, so you end up with quite a nice sample, which you could do laboratory experiments, permeability experiments on once you get it back to the lab. And rock core, which you can get by a regular core barrel, which you get by diamond drilling, either with a single wall or a much nicer, I'm not sure that is a multiple core drill barrel, which takes on this idea of the advantage of being able to keep the core away from the drilling fluid. In this case, the drilling fluid only sees it right here and then flushes back around the top again. And so in terms of contaminating the fluids, not so much. And if you're really worried about that, like some microbiologists might be when they're doing drilling for science, then you might flush it with nitrogen or some inert gas rather than actually water, which might contaminate it. So that's the guts of the sampling tools that you might use. I think we talked a little bit about what those tools are. This, I think, is only reiterating exactly what those things are again. This is a multi-tube core barrel by the looks of it, where the whole interior core barrel rotates. Yeah?
How, when they're drilling, if they're looking for a water table, how do they find the water table if they're using water to reduce friction?
If you're drilling with air, you'll find water because it'll blow back as a mist once you get there. Then you know your water. Water tables are often in the soil above it, but not always. So if you're augering, then water will rise inside the casing that you set, so you'd know that. If you're drilling with rotary, if you pull a drill string after you've gone a certain distance, I guess you'd find it. Also, I guess if you pulled the wire line, it would be wet to some length along the wire line, so you'd know from that. Yeah, you would know mostly. You might not care so much. I guess you might worry that you have more water losses above the water table, and so you might try and case to below the water. Bless you. You might try and case to below the water table so that you don't have to use. So if you don't have an easy supply of water, but certainly when you come off the hole, you can measure water levels as they recover. It's contagious. Okay, and you can measure them. And so. Yeah, so that's enough for these. So let's look at some pictures. See if we have some. I think this is kind of where we left off. I think this might have been the last slide we looked at last time. I'm not sure exactly what we've got here. This is the last form of drilling. Yeah, this is exactly what this is. This is the tool. This is the piston. The piston the shaft of the piston is in here. You put on here the Shelby tube, which might be another 2 feet on the end of it. You can see maybe if you trust me that this portion here is a bit of latex that goes against the wall to be able to guard against that. This is this is the piston in the bottom of the Shelby tube. This typically would be, and I have you can cut yourself on these pretty easily. So this is the syringe advanced, ready to go into the hole, as you saw, nice and pristine before it goes in there. deliberating something, I guess, still empty. Cleaning it off before it has the Shelby tube put on the top of it. Again with these coupling set screws at the top, and then you saw one that was beaten up before, but this one's pretty pristine. You can see the taper, I think, the cutting shoe, which is just a sharpened part of this tube, an existing sample or one still to be used. Often one way of classifying these materials is how strong they are. So stiff clays versus soft clays would be related to how strong they are. And so this is something called a torr vane, which is just a little torque wrench. So it's a little circle, the same as the size of a quarter, that has little protrusions coming out of it. You stick it into the end of the core, you twist it, and it's a torque wrench. It registers the torque that it takes to shear it off, and you can use that to classify the strength of the material, stiff clay or soft clay, which might be useful. This is kind of what it looks like. This seems a lot bigger, but you get the idea. This is the end of this thing that gets pushed into the end of the sample. These little flat windmill, not water wheel protrusions, if you like, grip it, and then when you twist it, they grab the clay, and when the torque gets too much to keep the clay, they just shear off the clay, and that's a measurement of the strength of it. This is the back step of the drill rig, paraffin wax, melted with a tiger torch, and then ultimately poured in the end of the clay sample to seal it in place. Seal the moisture content in place to keep it pristine for when it goes back to the lab. If you want to do experiments of it, you have it. And hot. Spill that on your hand, you know about it. I have. And then ultimately just capped off with protective end caps. Labeled, taken away. Coming off the rig, end of the sample, taking, actually turning the set screws in with an Allen key. They turn in, and this is just what the sheared off sections look like after it's been tested. Decoupled from the tool, torr vane is what it's called, just registers a magnitude. This is the maximum torque that it got before it slipped. Yeah, you see it there. Just very, very simple. A spring, a torsion spring that's standardized. Okay, something else I think. I don't know if the other ones. I think we'll come back to that. Any more that we want to look at? No, we'll look through those, but let's not do it now. Okay. So, what else? Let's skim. Back to this. So we've made the case that sampling might be a good thing because you know actually what's in the subsurface. If you're going to sample, typically you'd fill out a borehole log. And this is actually a borehole log for the Smithville site. Comes from Golder Associates. They still exist after 20 years. Is there a date on this? Yeah, 688. Don't know if these are done electronically now. It doesn't really matter. It's not the best place to have an iPad sitting on the edge of a rig. Okay, that's for sure. And so this is just a log of what's going on at the rig. So typically this could be filled out by the drilling helper, more likely be filled out by you actually, as the person on site, either as a, an introductory engineer or scientist or a technician position. And so all it is a depth log, something stated about, I'll just move across here, something stating about what the drilling method was. And so you know Smithville is a clay till that overlies limestones and shales. And so you see that the first part of this hole was drilled with a power auger, hollow stem power auger. The diameter, a casing was put in there after the fact and grouted in place. This is bedrock, and after bedrock it's drilled with a tricone and then rotary core drilling beyond that, so you'd get core recovery. So in this hole you have a hollow stem that's gone to rotary drilling, that's gone to diamond drilling, recovering core, all in the same hole. just as a progression. And the completion is given in the second column of HQ as the diameter of the core drill, and 96 millimeter diameter. HQ must be 96 millimeter diameter. NQ, HQ, I don't know what the classifications are. There's a descriptive log of physically what you're going through from whatever you get out of it. So from a solid hollow stem auger, you'd get stuff raised up on the flights. From the rotary drill, you get pieces kicked into your face as you stand above it. And from the rotary diamond drill hole, you'd get core out of it, which is shown here. The symbolic log would be a symbol to represent clay or shale or whatever. Elevations, some documentation of what samples were taken, how many, what type, and blows per 0.3 meters, metric Canada versus blows per foot. You saw the monkey hammer banging this thing into the ground. We said that this Tor vein is something that classifies the soils in terms of the strength, stiff or soft clays. Classifying sands, which you can't sample that way, is done by driving this split spoon physically into the ground. How many bangs with this hammer do you take to go 1 foot? Rudimentary, but there's 50 years worth of data that can tell you lots of interesting things about the soil from that. Not permeability, but lots of things about the engineering properties, strength. So the samples would be HQ rotary core, I guess this would be. It doesn't look like there's many samples, or certainly no blow counts in the material done on the top. No samples in the clays. In the samples that are taken back to the lab, what is the water content? What is the plastic limit? The amount of water you have to add to it before it becomes plastic. The test is you can roll it into a sausage that's 1/4 of an inch in diameter or something. The liquid limit is where you can add enough water. So I guess this is when you can dry it enough to roll it into a sausage. What is that water content? This is what is the water content you have to add until it flows like a liquid. And so these are both index tests for soils. And so these would be the measurements if it was a soil. And if it's a rock, the measurement would be in terms of how much core did you recover. So you drill 5 feet, do you get 5 feet of core, or do you get 3 feet of core? And so this would be the percentage of core that you recover. How much of it was solid in one piece, because that says something about whether you'd have fractures in there, which would be important in terms of its strength, but also in terms of permeability characteristics. RQD stands for Rock Quality Designation, which is the length of core in pieces which are bigger than 4 inches, 10 centimeters, which again is a measure of rock quality, as I guess the name suggests, rock quality designation. So used a lot in tunneling. If your rock quality designation is 0, it means all the core you recovered is broken to pieces, and if you drive a tunnel through that, it's going to take you between now and doomsday to do it. If you get 100% RQD, then maybe it'll go faster. So again, used as an index test to classify things. This is fractures per foot, I think. So this is how many fractures you get per feet. 1 fracture, 2 fractures, 0.1. And this is the dip angle. So if you get rotary core, you'd know if the dip was 90 degrees from the horizontal, or if it was 0 degrees from the horizontal. And that might be something of interest to you, is of interest for you, not so much in the things we're doing. What kind of fractures are they? Do they have bitumen on them? I think in some of these they talk about bitumen. Yeah, bituminous bedding in shales would affect permeability, I would think. Calcite, dissolved calcite, anhydrite says something about whether water might be flowing and whether water has flowed on that sample in the past. If you do some experiments in the lab, you might note hydraulic conductivity or permeability. Actually, in this case, it's really done for in situ tests. So we've made the case that you might want to take samples, but the other thing you might want to do is instrument the borehole once you have it there, and or do experiments in it to measure permeabilities. We talked about the issue of it being important to measure permeabilities at some scale. Big scale, large scales affect dispersivities, right? The bigger chance you have to contact a fault, big fracture, presumably the bigger chance for spreading, and also the bigger chance to get a large permeability might be. And so one way to do experiments is in situ is to take this partially cased well bore. The water table rises up to a given height. You pour a bucket of water in to raise it up another 3 feet, and then you just measure how long it takes to go back to that initial case, a slug test, so-called slug test. From that water drop with time information, you get permeability directly out of it. And so from these completed wells, you could actually do some experimentation to be able to measure hydraulic conductivity, which they haven't put here. This is the column for hydraulic conductivity, but you can do that. And the advantage of doing it based relative to taking a sample is that it's taking an experiment at field scale, not at laboratory scale, which might be helpful. And this is just a log on the right-hand side to say something about the instrumentation. And the instrumentation for this hole is that there's been a casing advanced all the way down to socket into the rock at whatever depth this is. It's been grouted in place by this plug. I guess first goes in the casing, the hole's open, you dump in some sand into the bottom. Sorry, let me revise that. You drill the hole, you put the casing down to lock it in, then you drill the rest of the hole for the rest of the way. The casing stops the top of the hole caving in. Once you've finished, you pull yourself off the hole. You drop a piezometer tube down here, which is just a piece of 1-inch diameter tube with some slots in it. You drop sand in around that piezometer tube to fill up the hole, so it'll keep it open. And then you drop either bentonite or grout or bentonite pellets into the bottom of the hole to fill this up. And then you have this completion tube go all the way up to the surface. So I guess in this case it has a hole that's cased, has a second casing inside that just sockets in here. It has a tube that goes all the way into this zone where you want to measure pressures and can run also slug tests to measure permeability at any time. And you seal this in by capping this, and then you can drop an instrument down here to measure the depth to the water table. If you're doing a test to measure permeability, all you do is you pour water into this domestic white plumbing tube, 1-inch diameter white tube. It raises the water level to some height, and you just record how long it takes to drop down with time. And from that slope of the rate of drop, it says something about how quickly it's flowing into the material around it. And you can convert that directly into hydraulic conductivity and permeability, and you plot that here. So this is the kind of archival record that goes with this. Some places, I don't know if it's done in Pennsylvania, Alberta requires that all drill core gets archived at a repository. Not so much for environmental stuff, but for energy cores. And also the records would go there as well. And ultimately, in these well bores, once you're finished with it, you might want to be able to measure pressures, as in a standpipe piezometer. You might be interested to measure permeabilities through well tests, Ludgen tests or slug tests. And you might be interested to take water quality samples as well, all in these completed regions. And so these are a variety of different piezometers that are used. So this is just a standpipe piezometer that we looked at in this previous hole. A porous zone with a pipe going out of it that allows water to flow into here up to some water level here that you can measure. You can add water into it to be able to look at the drop in water level with time and link that with permeability. And others, maybe more exotic piezometers like a pneumatic piezometer, which is just a membrane which has a pressure come down. So this is at the bottom of the borehole, this is at the base of the borehole, an inflow line, a return line, and I guess this, you pump air down into this. When the pressure in this air exceeds the water pressure acting against this membrane, then it bows this membrane. When it does that, all of a sudden you get a connection between this membrane and the return pipe. So only when you provide a pressure equal to the pressure at the base here do you get a return flow of air. And then if you know what the pressure that you apply that is, you immediately know what the pressure is in the wellbore. More usually they're electronic. Same idea, a membrane with a little strain gauge here. When the pressure pushes against this membrane, it deflects it. If you measure the deflection of this with a strain gauge, then you can use that to calculate the magnitude of the deformation, and you can calibrate this strain or deformation against the pressure. Exactly the same way the pressure gauge works, nothing more. And so you place this at the bottom of the borehole. And you can also do this in unsaturated materials where you have a net tension. So this is water, but it's at a negative pressure relative to atmospheric, and it's measuring the negative pressure in the water, which is in an unsaturated zone within the at the bottom of the borehole, in the vadose zone. And so piezometers of different kinds. More exotically than that, I've never ever seen these. Well, I have seen some of these. You can use borehole cameras. Borehole cameras, so you have an empty borehole. Maybe you didn't take core because you drilled it down really quickly with a rotary drill, just rammed it down, looked at some of the chips but don't have anything. What you could do is you could go in there after the fact with a borehole camera that just takes an image of the borehole as you go down, records it, it says exactly what's in there, and you get a stratigraphic log of exactly what's in there with time. You can also use these in interesting ways. If you think you have flow in your borehole, you could use it in one place to look at particles going past the lens. These tend to be really short focus lenses. They're not a lens that's focusing on you in the distance, but it's focusing, focal length is 2 centimeters, something, the borehole wall. And so if you see things that are moving in a static frame of reference, then you know you have flow in the borehole, and you know you have water going in somewhere and coming out somewhere, which is typically useful to you. So these are actually applications that would measure flow within the borehole. You can use a hot wire anemometer. Has a hot wire. If there's flow in the borehole, it will heat up water, which will then travel from that heated point across a sensor to go somewhere else. And so if you see something, heated water, coming across your thermocouple, it means there has to be flow in the borehole, and you can use that to be able to say something about the flow velocity. And so where it's flowing very quickly, you don't need to use this. But if it's flowing very slowly, which it might do, for instance, in boreholes in crystalline rock that you're using for to scope out a radioactive waste repository, which you want to have really low permeabilities, then that might be a way you do it. This, I think, is the same kind of sensor, a hot finger in the middle, thermocouples around it, you heat up the stuff in the middle, and you see if it arrives quicker at one of these fingers. If it does, then it's going in that, flowing in that direction. And so all of these are kind of exotic methods. Some discussion of what's good about piezometers and what's not so good about piezometers. I don't think I'll go through that. But this is basically the idea of a multi-level piezometer. Pretty simple, the idea. You drill a hole. The hole goes down as deep as you want it to go. You might like to have lots of these nests at different levels to measure independently in these different zones, maybe in a whole series of aquifers, exactly what the pressures are, or do pump tests or flow tests to measure permeabilities in these zones. So the way that you can get multiple zones within a single well is you go in, forget about these lower standpipes, you block the well with bentonite, so you can get these little pieces of pressed swelling clay which have lacquer on them, which are about the size of your tip of your pinky. You drop them down the well, they go down to the bottom, the lacquer dissolves off, bentonite, swelling clay, it expands, and it basically makes a seal. You drop a piece, maybe 100 feet, maybe it's 800 feet deep. You can certainly do these down to 800 feet. I have done. Which is just a piece of this 1-inch diameter pipe, which is fed all the way to the bottom. A hacksaw takes cuts across the end, maybe at 1-inch intervals, just to cut across this to be able to let water in. you drop sand or gravel from the surface down the borehole to pack this zone around it. And then you drop these bentonite, peltonite, trade name pellets on the top to seal it. And you've isolated a zone with this going up all the way to the surface, so you can drop a water level indicator in it or fill it up with water. You grout the rest of the borehole up to the next section that you want to do, and then you repeat it by dropping another piece of tube down to the bottom and just repeat it. So then you have a whole bunch of these nests with as many tubes from this coming to the surface that you can individually test as time goes on. You can't remove it, it's left in the hole, you don't necessarily want to remove it. The other way to do that, where you can remove it, is to do experiments with what's called a straddle packer. So the kind of the same idea as this, you want to isolate this zone here. So you want to isolate this zone so that it's separated from the borehole below it and above it. But instead of having this permanent seal, use a packer. So a packer is a mandrel, which is just a tube that has on the outside of that tube a neoprene sheath, just like the stuff you'd use for a wetsuit, if you've ever seen a wetsuit. And it sits on top of this mandrel, has a nitrogen line that goes up to the surface to a nitrogen tank. You inflate the pressure in the line, and it just pushes this sheath off the mandrel against the borehole wall. If it pushes against the borehole wall, it's just like inflating a balloon in there, and it seals it. The same here. One inflation line going to the top packer, one going to the lower packer. It has a straddle length in between them. It straddles a zone. And in this zone is just a length of electrical conduit, basically, with drill holes in it to let water out. And you can inflate both of these packers to seal off the top and bottom part of the borehole. You inject water in here, measure the decay of water level as a function of time, and you can use that to, basically the only place it can go is out into the formation, and you can use basically the head versus time curve as a measure of permeability. So I guess you could imagine that if it goes down really quickly, this would be a high permeability. If it goes down really slowly, it would be a low permeability. And there's moderately sophisticated equations to be able to do that. When you've done your tests, you just drop the pressure, these undeploy, I guess, and then you just pull it back up through the things. So you could actually go through your whole borehole, doing every single stage along the length of it, as much patience as you have, using a 3-meter section, using a 1-meter section, using a 20-meter section, and you could actually use it to look at the statistics of permeability as you go up along the length. So you can measure it. You could, actually there's one very well-known sampling technique, the Waterloo piezometer, which actually uses this kind of idea where you get pre-manufactured a long stem, and that long stem has on it a bunch of these packers. So it might have a packer here, and here, and here, and here, and here, and here. And it might have a sample port that goes in here, and here, and here, and here, etc. It goes into the borehole, and then once it's in the borehole, you pull a clip, and these individual packers just inflate. Except they're not packers with a gas in them. They're actually packers that have some kind of two-component fluid, the kind of insulating foam that you see people put into the side of their houses. The two components mix, it foams, it inflates the packer, and it never deflates the packer because it physically hardens in place. And so you're left with a sample that will actually isolate a zone and allow you in this zone to take water samples of whatever you like to be able to look at. And all of these zones will be individually packed off, but packed off permanently. This never comes out. This is a tool that you would use to actually retrieve. So again, things that you would actually use to be able to make measurements with. I think suggestions of different casings, kind of boring, don't want to talk about that. Other methods. Yeah, so let's go on. I don't think I have much to talk about in terms of those different piezometer methods. But the other kinds of sampling, so we said that you can drill holes. The holes matter whether you're in soil or rock. It's either augers or rotary in soils. It's either rotary or diamond drilling in rocks. We'd like to sample from them. We'd like to instrument from the boreholes because we put something in place that is quite valuable to us. And the final way of doing this is by what's called direct push methods, where you don't physically withdraw anything. What you physically do is you push a rod into the ground and keep on pushing that rod into the ground. And you could imagine using that to measure a couple of things. You could measure how much force you have to put into the ground as a proxy for how strong the rock is. You could use it as a measurement, if you could measure how much friction there is on the sleeve of that, to measure, for instance, if it's a sand or a clay. Sands would be very frictionally resistant, clays would not. Grab that, get your foot. And you might want to measure pore pressures that you generate at the tip or that were present in place at the tip as a measure of them. And so these methods are sometimes referred to as cone penetrometer tests. That's what they are. They're now also marketed by companies like Geoprobe as direct push methods. And the basic idea is you physically push a rod which has an end area of 10 square centimeters. So I think it's 1.25 inches diameter. You could work it out. And it's just physically pushed into the ground. It's brought to the site on a cone truck in some cases. It's a whole bunch of drill steel, typically in maybe 3 feet or 1 meter sections. This is one of them here. It has a tip attached to it that has a pressure transducer to measure pressures. It might measure the sleeve friction on this length here by having a load cell that measures the load here behind the sleeve, and a load cell that measures the load here on the tip. So if you have a load here and a load here independently measured, this one will measure the tip resistance. The difference between this one and this one will be the amount of friction on this segment. So you can measure how frictionally it's resisted, a measure of sands, and what the end bearing of the clays might be to be able to make some distinction. And it can measure the pore pressure, typically in a transducer, which is right on the shoulder of this probe here. And so this is kind of the business end of this probe, which is on the end of this steel here that goes out of the bottom of a truck and into the ground. It has the load measuring things and the load measuring cells and the pressure transducers electronic, so there's a signal that comes from those. And so this is the cord that comes up from them. And as you can imagine, you're going to push this thing into the ground by pushing this down. It'll go down to the bottom of the truck. You'll add another length on it. That length, of course, has to be pre-threaded with this thread. And so here you can see on the side, not very well, there's the cable that goes into all of the lengths of the tube, which is pre-threaded. And you just put one on the top, screw it in. This press cycles back up to the top, clamps on, and then physically pushes it down at 2 centimeters a second, constant rate. And it measures those characteristics at the bottom. And very straightforwardly, what it does is, if you can imagine measuring the load that you have at the tip of this probe, the magnitude of friction that you measure at the side of the probe, these are two measurements that you can make, and you make them continuously as you go down. So at any particular depth, you have a measurement of this end bearing and friction, so two numbers, so you can plot it somewhere on this probe, on this chart. If you know where it plots in terms of a zone, you can use it empirically to say that what you're going through is sandy silt to clayey silt, and you can also correlate it with things like permeabilities. Likewise, if you measure the pore pressure at any particular depth and the end bearing, again you'll end up with a point here, and it will again tell you something about the materials that you're going through. So a very powerful method to not take a sample, but by empirical relationships, experience, correlations, say something about what the material is that you're going through, and to be able to profile it very rapidly. And so a typical trace would be it sits on the ground, it physically pushes this thing down into the ground at 2 centimeters a second. With depth, it gives you a measure of this tip resistance as you go down through here continuously. It measures the frictional resistance as you go down through here continuously. It measures the pore pressures as you go down, again, continuously. So if you look at it, I keep getting cramps in my hand. So if you look at this at any single one depth, then that gives you the parameters to plot on this curve, which would tell you exactly what you're going through. So you could end up with a plot that gives you a no pun intended, blow-by-blow account of exactly what you're going through with different depths, and also attempts to attach a characteristic to them. And the characteristic of interest would be something that would relate to permeability in our case. So I think the next thing that we're going to look at on this was that. Perhaps not. Yeah, okay. Here's one of these things in action. A very short one. Oh, you can see most of the parts. You'll see a better one. So this is the sensor cord. Don't know where the tip is here. It's being threaded through the tube that's sitting on the ground in this particular case. This is a portion of it already into the ground. This is just a photograph, I guess. Okay. This is a geoprobe rig. You don't need a driller to operate it. You buy it for a couple $100,000, I would think. This is the gantry that you physically push the rods down through. Let's see if they're actually going to show us. This is the probe. Unceremoniously, you can see what it's in. It's this is the pore pressure measuring part. This is a load cell behind here. This is another load cell here. It's saturated with silicone oil, so that there's no air in it. And then once it's saturated and de-aired, it's covered with a condom in this particular case, as you can see. And that's just physically pushed into the ground. As it goes into the ground, this condom just gets ripped off as it abrades against the ground, but it means that when it goes into the ground, it actually is saturated, so you don't get strange results. And I think, well, this is 5 seconds. Let's see what we see. A bit frantic. Don't think you see very much. You see someone's feet. I think there's a better one here. Maybe not. Ah, yeah. 32 seconds. So you see the tip here. It'll go into the ground. I guess these aren't tips. This is the screws that anchor it. So these are just little screw piles. This will go onto this arrangement, and it will be physically pushed down the ground by this gantry going down. And then as soon as it reaches the bottom, before it reaches the bottom, you'll screw another length onto this. And then as soon as it does reach the bottom, this will quickly cycle back to the top, grab the top, and then push it through. So yeah, you see that. So movies are best, I think, for this. This is in Izmir, Turkey, where they had an earthquake. Don't pick your backside when you're doing it on camera. So this is being pushed into the ground at 2 centimeters a second. I don't know if you'll see it all the way through it. This is a site of an earthquake more than 10 years ago, maybe 15 years ago. Killed 20,000 people through liquefaction and houses falling over. And this is a site characterization tool looking for places that are susceptible to that kind of failure where the ground liquefies and houses fall over, or it amplifies the shaking and it's much more dangerous. And so, yeah, so we didn't see so much there. Don't need to see that. Come back to that. This is the same one of these things on a slightly different rig. I don't know if this is playing. Oh yeah, bit of atmosphere there for you. Same deal. This is in Delaware. in this particular case. Does F do it full screen? A bit too artistic, or maybe autistic in this. So you can see this. So this guy was the representative of Hogentogler who market these things. Actually, this is exactly what you see. Okay, so this is one of these probes. This is actually a different probe. This is a little CCD camera, just like the camera in the computer. The light stuff on the side are LEDs to illuminate it. And the whole idea here is this is called the vis cone. So this is maybe a meter behind the tip of the cone, but as it goes through the soil, it illuminates the soil to see exactly what it's going past. And so you get a continuous movie of the soil as it comes past this window, and you know whether it's a sand or a clay or a silt or whatever just by looking at it. Or you can see if it has denappelant as well as it squeezes past. Really very curious equipment. So this is deploying that piece of equipment at a field site in Delaware. This is the year of Katrina, so is that 2004 or 2005? I can't remember. In August, but before Katrina. So this is the mast that raises this thing. I don't want to wait all day to be able to watch this. This is the screen that looks at whatever's going on into the ground. Probably don't see very much. Because of the sampling frame rate of this camera versus the display frame rate, you get this flickering, which I think destroys it. This is the cone, just as you saw before, except instead of having a condom on it, it has a piece of bicycle inner tube around it, which makes sure that this circular section around the tip, the heel of the tip, this portion where the cone, bless you, goes into the cylinder, which is where the pore pressure measurement stays saturated. This is where a load cell is that measures the frictional load on this portion. So there's a load cell in the base that measures the load on the tip, and hopefully this is just going to be physically pushed into the ground. And so, very straightforward. You just basically advance it at 2 centimeters a second. As it gets pushed into the ground, you measure the end bearing, you measure the sleeve friction, the difference between this load cell and this cell has to be the friction on this, and you measure the pore pressure. And you use that to correlate with whatever the materials are that it's being pushed through. Let's see if we can see it in action. Oh, you saw that. Some grad students. This is the A-rod with the cord threaded through it from one end to another. You see it's just regular male-female fittings to be able to do this. Again, you always rotate them clockwise. You never have to rotate this. Must be going into the ground now. Deliberating things. Still not gone into the ground. Maybe about to go into the ground. Try to look to see it in action. Oh, this is doing so. It's actually in the ground, and actually we had some special tips on it that will allow us to do these kind of pump tests, flow tests, by filling the rod up with fluid, having it flow out of the bottom, measuring the decline, and using that as an index for the permeability. I'm looking to see, there's the tool. I wanted to see it being pushed into the ground. I don't really see it being done that way. Oh, that's... oh, yeah. I always used to bunk with the grad students, so he's taking a picture as we were sharing a room. I don't see one of it being pushed into the ground with the stage. Well, yeah, it's quite straightforward. So you grab this thing at the top, you push it into the ground with this stage that goes down. As it's going down, you're screwing another 3-foot length onto it as it's going down, so that by the time it gets to the very bottom, you stop. Then it takes a couple of seconds to pull this thing back up to the top, grab onto the top again, and then repeat. And again, as it's coming down, you put on another 3 foot of cord. Oh, you see this going in. So maybe this will be the only chance we have where it I hope it's not actually overdubbing my voice as we go in there. It may well be. So. Stops briefly. Maybe don't know if it stopped for any reason other than this is the the change in stroke, going back up to the top and resuming again. Doesn't look like it. We're waiting for it. Yeah, so you get the idea. You saw at least a bit of that in the previous case. Yeah, okay, so that's enough. So, direct push. So, used a few times, Rachel Brennan in civil engineering, I think, has brought some of these, had Geoprobe, who are based out of Salina, Kansas, come on campus with these things. Different from this rig. This is University of Michigan's rig. It's owned by Rowan Ritsu, one of the guys here. I think the guy up, actually the guy in the white hat on the left-hand side is a professor there. And it's truck mounted, needs some amount of skill to be able to operate it. But these are Geoprobe rigs you buy, and a technician can basically operate them just by running it on the back of a trailer that gets trailed around to a site, and actually can be driven inside buildings as well. And so, I don't know, some other random pictures just to look at some things. What else we got? Just for the heck of it, let's look at these. So we've talked mainly about DNAPLs, but another big part of groundwater are things like radioactive waste disposal. So this happens to be an experimental tunnel in Korea, South Korea, in Daejeon, looking at proving out sites, not this as a site, but proving out instrumentation to measure pore pressure changes in rocks. And so this is a tunnel that's driven into a mountain and then instrumented to do things like tracer tests, where you inject a tracer into the ground and you measure its arrival in different places, measure stresses, measure how permeabilities change as a function of stresses, because when you put hot waste into the ground, it heats up the ground and it stresses the rock, and it may change permeabilities. And so these are just a bunch of field experiments. This is a experimental tunnel, not in Korea now, but in Mizunami in Japan, which is in granites. Again, an experimental site for radioactive waste disposal. Not for radioactive waste, but to do experiments that look at tracer tests. A pristine tunnel, very Japanese. I think these things are all there to capture the moisture so it doesn't drip on you. And this is just a bank of sampling locations, a whole bunch of piezometers, well bores that go in from the tunnel into the rock. You pump in, say, a tracer, and then you measure the arrival of that tracer at a bunch of locations, mainly by doing syringe sampling on capillary tubes to be able to pull stuff back from those sampling locations. Piezometers that aren't any different from the ones that we talked about in this class, that are just a zone that's isolated by packers above and below, or by bentonite above and below, from which you can take samples and be assured that that physical sample comes from that isolated zone, not 400 feet further along the borehole, because you physically isolated that region. So in this case, I think just getting a sample out along tubes. This is the borehole. Looks like it goes 100 meters into the rock away from the borehole. This is a Switzerland, Monterrey lab. This is in shale, which is an analog, actually for two things. It's an analog for the caps of three things. Caps on petroleum reservoirs. What's the permeability of these shales? How do they get affected by fault reactivation? Secondly, this is the Swiss candidate material for radioactive waste disposal. Put it in opalinous clay because it's really low permeability. And also it's unloading after an ice age, so all the flow of fluids, as it unloads and it kind of expands, it sucks water into it. So if you have fugitive emissions from radioactive containers breaking open, they don't go outside, they go inside, just like, as I found out the other day, the US Capitol is overpressured slightly. So if you have agents come in, biological agents from outside, they can't get in there, just like nuclear plants are under pressured. If you have a release in the radioactive plant that doesn't blow to smithereens, then that release gets contained because it's under pressure. All the airflow has to be from the outside into it. So I didn't know that about the Capitol building. And the third relevant activity now is that shales are actually reservoirs for gas. And so understanding the hydraulic properties of this. So this is just coring in this particular underground research lab, which is in the northwestern part of Switzerland, in the Jura, and is used for a bunch of underground experiments in Addis. It's an old mine, I'm not sure for what, but here it's used to be able to look at measuring permeabilities, seeing how permeabilities change with stresses, doing tracer tests to see how fast flow occurs, looking at borehole breakouts to see what the stability of wells might be that you put radioactive canisters into to see if they'll fail. To do fault reactivation experiments, and also to do full-scale experiments where you take an assembly of, not real in this case, reactor rods, the fuel rods that go into reactors, place them in an array, place them in a cask, and then put that cask within a tunnel, and then backfill this tunnel with bentonite, and that would be the form of a typical repository in some of the European programs. So this is an experiment to look at how this bentonite resaturates over time, how it works to work as an effective barrier so that if this breaks open, nothing spills out. And so this is that's a full-scale test. Full-scale test to be able to do this. Not with real material, but to look at this, the resaturation of this. That was a model of the test in situ, and this is the actual experiment in place down at the bottom of an adit. What else? Same thing. You see these bricks are of pressed bentonite, which are the backfill, which seal it in, which once they get wet, they swell up in exactly the same way we talked about putting peltonite pellets into the bottom of a borehole to seal off a zone. And this is just a rail. All the data acquisition comes out along here. This is the train that you push yourself along sitting on to get down here by pulling yourself along the inside, not motorized. St. Barbara, right? Patron saint of miners. You always find these underground. And this is again an underground experimental site, this time in granite, in Grimsel, in the southern part of Switzerland, in the Alps. And in this particular case, these are experiments to look at flow. It's in the, okay, we know that. This is to do flow experiments in fault zones. It's actually in the base of a big arch dam to measure displacement along fractures as you load them, to do permeability tests, to take cores, to do in situ again to do bentonite backfill experiments in granite in this time. In this case, this is a big packer. So we said before that in a borehole you have a mandrel with neoprene sleeve around it and you inflate it to be able to seal the borehole. This is exactly that, but a much larger scale. This is 2 meters tall. This is the inside mandrel. This is the packer on the outside. And it's to be able to seal off a big fault zone so that you can do injection into the fault zone and measure flow rates. The fault, so the packer is here, the fault cuts across it in some way like this. And this is to do experiments inside that. Don't know what that is, doesn't matter. So, in situ experimentation to look at rates of transport in these systems is important. These are packers. So this is a neoprene sleeve on this mandrel with a zone in between it. Set up in place. Beautiful rock, lovely granite, lovely crystals, and just a dam site. And another underground research lab in what used to be the French deep base for missiles to reply to a presumed first strike. and so now being used for something else. So this is the zone within a packer. This is the zone which you'd flow water into. Above and below it you have these neoprene packers that you inflate. This is the inflation line to be able to pump nitrogen under pressure into this packer. And this is the packer waiting to be deployed. And these are the rooms in which the operators who are going to press the buttons for the missiles that would destroy the planet used to sit in. We've come full circle. So we'll leave it at that. So really all we've talked about are mechanisms to be able to take drill holes, which are very expensive to get the most out of them in terms of what we understand by sampling, be able to instrument them, to be able to understand what might happen in the future, and also use direct push technology as just another way of being able to profile, but only in soils. Next time we'll talk about geophysics to be able to round this out as our final foray, if you like, into site investigation.